Okay, so let's try this guy. Let's do. Nope. Okay, so let's find, remember what we're doing, we're trying to find the absolute extrema of that function on that interval, right? Okay, so first of all, for that function, where are the implied parentheses? You should always add the implied parentheses. Yeah. Okay. So what do we do? Okay, good. We're going to differentiate because we've got to find all interior critical numbers, right? By interior, what do I mean?
Within the function, excluding the endpoints.
Okay, yeah, within our domain.
There you go.
Good. Okay. So we want to find all those critical numbers, right? Now, critical numbers are related to the derivative, right? Okay. So let's take the derivative, and then you tell me what to do with it to find the critical points, or the critical numbers, we'll say. Critical numbers are the values of x, and the critical points are the ordered pairs, including values of y. So what's our derivative?
Negative sign.
Say it again?
Sign. Negative sign.
Negative sign.
X
Times
is it
pi. Okay, make sense? Okay.
If it was negative sign, if it was cosine xy, would the derivative would be the negative sign pi y times sine y prime, right?
If it was cosine pi y,
Yeah.
then it would have been negative sine pi y times y prime outside.
Times y prime, not.
Yeah.
Okay.
Yeah.
Then you get rid of the pi.
Times pi y prime. Sorry, pi would have been up front. Yeah, you're right. Okay, does that make sense? Okay. Okay, so what do we do with this? We want to find critical numbers. Where's one place I look for them?
Endpoints.
No.
Where
Critical
it-
numbers.
Where it equals 0.
Okay, where the derivative equals 0. So f prime equals 0 when what? And this is something I like to do. I like to try to use language like this, like the derivative equals 0 when what is happening. And sometimes the thing that's happening can be simpler than rewriting an equation in terms of everything. So when is this is going to equal 0 when sine equals 0, right? Does that make sense? Because we're just multiplying it by some constant, okay? When sine of pi x equals 0, okay? Well, when is that true?
That should be negative sine pi x or maybe positive sine.
Doesn't make any difference because the derivative is going to equal 0 when sine goes to 0, right? You see what I'm saying? Do you see why that's just a little bit easier? A lot of times there's going to be one critical part of a function that's going to make it go to 0. And we really only need to focus on that part. You see what I'm saying? So using this kind of language, you see how that's, rather than just setting the whole derivative equal to 0, we can say, well, the derivative equals 0 when that happens. Okay, and then we have something easier to deal with to find the critical numbers. Does that make sense, what I'm saying? Okay. So when's that true in general then? When is the sine of pi x equal to 0?
when X equals 0?
When x equals, in fact, let's just be totally general with this, and then we'll look for the places on our domain where it happens.
Not just any positive, any integer.
Any integer, isn't it? Because if we look at our unit circle, sine equals 0, it's the y coordinate there and there, right? Think what those are. 0, pi, 2 pi, 3 pi, 4 pi, or whoops, if I go back the other direction, 0, negative pi, negative 2 pi, negative 3 pi, just any integer multiple of pi, right? So that's true when x equals n, where n is any integer. Okay, so now where does that fit into our domain? If x is greater than or equal to 0 and less than or equal to 1/6, where's that happening?
At 1, or no, 1, 0.
It's 0, right?
Yeah.
0 is an endpoint anyway, so, okay, I guess I could kind of say for us, that's when x equals 0, but because it's an endpoint and we're looking for absolute extrema, we'll come back in hindsight and look at whether we had to even write that down. Okay. What's the other place where we look for critical numbers? Where what? Not critical numbers. Those are different. Well, let's review what critical numbers are, right? Critical numbers are related to relative extrema, right? Critical numbers are every relative extremum. And what's a relative extremum?
Extreme in a certain area.
Within the endpoints.
Say it again, Brandon.
Extreme in like a certain area.
Okay, so it's going to be the highest or lowest point relative to it locally speaking, right? In the region of that point. So what do they always look like topologically? Peaks or valleys, right? Okay, so in mathematical terms, they would be minima or maxima, right? Okay, so a relative extremum is a peak or a valley, right? Where do peaks and valleys always occur?
Functions.
At critical numbers, right? At places where the derivative is either equal to 0, which results in topologically what kind of peak or valley?
Just the tangent. So
Okay, so it's good. Yeah, so a smooth one,
yeah.
right? Or at places where the derivative is undefined, which could result in what kind of a topological shape to our peak and valley? Sharp, right? So jagged, okay? Do all critical numbers necessarily yield extrema? Relative extrema? No, they don't have to. But every relative extremum must occur at a critical number, right? Does that make sense? So then this kind of falls in line with our strategy for finding absolute extrema on an interval then. Where could they occur? The highest and lowest places could either occur at peaks or valleys or endpoints, right? We're always going to check the endpoints, so do we really need to include a critical number that's an endpoint? No, because we're going to check it anyway, right? See what I'm saying? So we really only need to look for the interior critical numbers. So that one's kind of, don't really need it. Okay, are there any places where our derivative is undefined? No, if we were to graph, and there's a couple ways you can think about this, right? We can always think about this in terms of what are the two traps we could fall into that would cause it to be undefined. Dividing by 0 or
Root of a
Even numbers
negative.
for-
even root negative number. Neither of those show up in here, do they? Okay, another way to think about that is just in terms of the graph, right? If you've taken trig, and so you know that a sine graph and a cosine graph, those are both well behaved. They go forever and there's never any asymptotes or breaks, right? You would never have to pick your pen off the board if you're going to draw a sine function. Whereas tangent function you would, right? You've got these big sweeping asymptotes, right? So we know then, because this is defined everywhere, that the derivative is defined. Yeah, that the derivative is a sine function. And so f prime is nowhere undefined. And so this problem gets pretty easy. There are no critical interior numbers. So what are we really comparing? It's the endpoints. Yeah, that's it. So in our table would just look like this. There's the x-axis. Make a column for y. And a column for y prime doesn't really do anything there, but it could. It could if we had interior critical numbers. And then our domain went from 0 up to 1/6, so there's my interval on the x-axis, and there were no interior critical numbers. If we wanted to include that 0 there, we could, but it doesn't really do anything for us because we're going to check those endpoints anyway. And then all we do is just complete the ordered pairs. Find the y values that go with those x values, and what can you tell me about what's going to happen here? Are any of them going to be left without a prize? No. Right? Defend that. If we give prizes for the relative minimum, or for the absolute minimum and the absolute maximum, both of these guys have to get a prize. How come? There's only 2 possible points, but what if could they both be like, what if they both were maxima, and then they wouldn't get a complete prize? Can that be the case? Could they both be absolute maxima?
But not in this one.
They can't in this one either. How come?
Because they have two different y values.
Say it again.
You have 2 different y values for both of the functions.
Pretend we didn't, though.
Okay.
Or, I mean, okay, pretend we didn't know that.
Oh. Figure it out.
Okay, but there's a reason they couldn't possibly, without even having to do any evaluating, there's a reason just logically that they could not both be maxima.
Just because of the way the sign.
Still could be. I mean,
Just
but
because of
what's
the way
wrong?
the graphic-
Make a sketch. What's
It's
wrong
not a
with this?
straight
If,
line. Well,
Just
yeah, it's not a straight line and there's no
Last
critical points. We know it's not a straight line
uh-huh.
and there's no critical points in between.
Oh, there's no
You can't
critical
switch.
numbers in between, so what's that mean?
That means
If
you
they
can't
were
loop
both
back.
maxima,
They
what would
can't
have to be in between somewhere?
critical point.
There'd
Or
have
a
to,
jagged edge.
there'd have to be a minimum, wouldn't there?
No.
Right?
Or maximum.
If the function is continuous, which it is, right, then there's no way that I could ever possibly go from this point over to this point if they're the highest. There's no way I could go from there to there without having some lowest point then, right? Agreed? There would have to be at least, if these were absolute maxima, there'd have to be at least one intervening minimum, and there were none, and we proved that. How did we prove it?
With the zero trig
Well-
definition derivative deal.
We proved it right here. How? You already said it once.
No
Zero.
critical numbers.
There were no critical numbers, right? And if there were no critical numbers, there cannot be any relative extrema there, right? Make sense? Okay. All right. 4, oh, what am I doing?
Crazy.
What's wrong? My geometry class is gonna love that when they see that stuff. All right.
Can you just start teaching them that and see if anyone stops you?
Yeah, just tell them it's geometry.
Yeah,
They'll probably believe you.
that would be a mean thing to do. Wouldn't it? All right, so for today,
I think he's talking about string theory.
I want to just look. Today's really short. I want to look at two things.
The meaning of life.
Meaning of life. Yes.
Algebra
No.
What am I even doing?
Let's do some algebra
Trying to
1.5
find-
stuff.
Yes.
I think.
Let's see how fast we can get through the
think that's a
algebra
good break, some
curriculum.
algebra.
Yeah.
Finish the whole thing in 20 minutes.
Okay. So.
Hey, there's the book.
Oh no.
Yes.
Oh no.
Wait, this is AP edition calculus?
Well, yeah, essentially. I mean, this now they have different books for, but yeah, we do everything in this book.
What was it?
So, this class, can we define this class as an AP class? Mr. White?
I think so.
It
Okay.
counts for the honors diploma.
Well, yeah, it does,
Mhm.
but like,
So does.
Oh, like on
House.
college
yeah,
applications?
stuff like that.
No, it's
Oh,
just
no,
straight
yeah.
I didn't count it.
You can't just go from taking like this trig to AP calc.
Okay.
Why not?
So here's what I want to look at.
It's high school AP calc.
I want to look at two things today. So let's look at these two existence theorems, right? These are called existence theorems because all they say is if you meet this criteria, then something exists. Now you still have to go do the math and find it, but it exists. So Raleigh's theorem just says if f is continuous on the closed interval, and pay close attention to this because this is something we're going to define this in a different way that's really cool. If f is continuous on the closed interval, a to b, and differentiable on the open interval, a to b, then if a equals b, if f of a equals f of b, then there's got to be at least one number c in the interior interval such that f prime of c equals 0. So let's look at that. Now there's two things I want to point out here. One of them is a new way of saying something here. Somehow I lost, how do I, oh man, I know I'm supposed to see that.
Mark is already on Christmas vacation.
Right click to change.
I think we should spend the rest of the period messing with this, the projector.
Sketchpad.
I'm right clicking. Why is that not? Oh, there it is. It's on the other page. No wonder. Huh. Didn't see it. No wonder. Okay, let's see. I want that color. Come on, why didn't it do it? I need more colors. I lost a color. Oh, there it is. Okay. So, okay, so let's, oh, that's still not the right color. That's gotta be, that'll,
This is gonna be
That'll
good color.
all right, yeah. Okay, so let's take, you'll see why in a second. So let's take this statement right here. And this statement right here. And let's combine those. What's it mean to be continuous on the closed interval? Means I can draw it without doing what? Picking my pen off the board. Okay. What's it mean to be differentiable?
You can take the derivative.
Okay, yeah, it means take the derivative of all, right? Where can't I take a derivative?
Try the sharp corner.
Ah, sharp corners. And then the other places where we couldn't take a derivative would be things like vertical tangent lines. Yeah, that one's a little weird. But the other places would all be places where it would be discontinuous. We already know it's continuous, right? So really what this adds is that it doesn't have sharp corners and we don't pick our pen off the board, right? And then we have to always kind of look out for vertical tangent lines, but they don't show up very much. So the way we could describe both of those together, there's a word for it. Smooth. That's what mathematicians call it. Not in this textbook, but when you get to college, we call it that. So you almost start calling it that. Smooth means continuous and differentiable. So in one condition, you get both of those, right? Smooth, and it always just implies it's continuous from the left endpoint to the right endpoint, and there's no sharp corners in between the endpoints, right? So if it's smooth, and f of a equals f of b, well, those are just y values, right? So if the y values at the endpoints are equal, then what does that tell you about the slope of the secant line connecting the endpoints?
There's at least one derivative that's 0.
Well, if they're horizontally aligned, what's going to be the slope of the segment connecting them?
Reciprocals.
What?
Are there reciprocals?
No, like look at this picture right here. We don't know what A is and B is and f of A and f of B, but that could be f of A and that's f of B, right? So what's the slope of that segment that connects them?
0.
0, yeah, right. Okay, then all Raleigh's theorem says is if the function is smooth, there has to be at least one point on the interior, call it point C, or value C, where the tangent line is flat. Okay, that's really all it says. It's that f prime of C, the slope of the function at C, equals 0. That makes sense, doesn't it? There's no way that you could avoid that. If I don't have any sharp corners, right, then I either have to, unless this is just a straight line itself, in which case every point has a flat tangent line. But if it's not a straight line, then it either has to have at least one maximum or one minimum, and possibly more than one, right? And at a maximum or a minimum, that's going to be a place where if it's a smooth function, it can't be jagged, right? Then it has to have a horizontal tangent line. Okay? Make sense? No big deal, nothing so profound. And then this is what we call an existence theorem, because it just says that if it's smooth on that interval and the endpoints have the same y value, then there's got to be at least one number c where it has a horizontal tangent line. Now go find them, right? Now you have to do something else to go find them, but at least it tells you that that there's the guaranteed, the existence of at least one place like that is guaranteed. Okay, what's more interesting though is if we take Raleigh's theorem and we just kind of turn it sideways. Okay, we allow it to tilt. And then what we come up with is something better called the mean value theorem. Okay, the mean value theorem is the same thing as Raleigh's theorem, only this time we're not going to, part of the criteria is not that f of a equals f of b. We're just going to take f of a and f of b as being different in general, right? Then the outcome of the formula, or the outcome of the existence theorem is going to be that instead of guaranteeing a place where the tangent line is horizontal, there's got to be at least one place where the tangent line has a slope equal to the slope of the secant line connecting the endpoints, right? So what does this say? If f is smooth on the interval from a to b, continuous and differentiable, then there exists, that's all we have to say, then there exists at least one number c in this interval, a to b, such that the slope of the curve, meaning that the tangent line to the curve, the slope of the line tangent to the curve, is equal to the slope of the secant line connecting the endpoints. Make sense? Okay, and that's really all that is, the slope of the secant line. F of b minus f of a is just change in y or rise, right? And b minus a is change in x or run. Just rise over run, isn't it, between the endpoints? Okay? So how do we use this? Let's look at a couple examples here of how this is useful to us. Let's look at, for today I think we're going to run out of time, so we'll just look at a couple math examples, but then start of the period tomorrow we'll look at maybe some actual physical examples of where this could be useful.
What about the geometry thing?
Oh, if we have to, yeah, we got to do that too. I don't know if we'll get to it today.
That's a good 3-minute thing, probably.
So let's just pick, while I'm here, I might as well just get one out of the book.
No for me.
Let's just pick one like these. How about if we do 41? Okay, so I omitted the instructions, but really all this is saying is show that the mean value theorem either applies or does not apply. Well, it applies because the function is, we just have to look at the function and see if it's smooth on that interval. And if so, find the values. What's it want you to do? It wants you to find the values, all values of c in the interval a to b such that slope of the tangent line equals the slope of the secant line. Okay? So is this continuous and differentiable? Well, it's continuous. What's the derivative?
3x squared plus 2.
Okay, I want to make a connection here. Differentiable means take the derivative of all, right? Okay. If this is the derivative function, what would happen in places where it was not differentiable?
Divided by 0, or the even root.
Yeah, something would have to happen to this function to blow it up, right? So do you see, this is really cool. Pay close attention. This is one of those things that just, I think is so cool. We are applying the same criteria here that we did here when we looked to see if it was continuous, right? What are the kinds of places where it would be not differentiable? Those would be places where the derivative jumped, right, or wasn't defined. Does that make sense? Okay. Is that happening? No. This function is continuous, isn't it? If the derivative is continuous, that means it's differentiable, doesn't it? Does that make sense? Okay, if the derivative is, if I could draw the derivative function smoothly without picking my pen off the board, then, I don't even have to be smooth. It could even be jagged. But if I can draw the derivative function without picking my pen off the board, then that means that it's continuous and therefore the function is differentiable. Agreed? Okay? So store that one away. We'll rehearse that again. But when are we out of here?
Right, thank you.
Oh, jeez. 30 minutes doesn't cut it for calculus. Finish it up tomorrow.
45 barely.